Welcome to Maths with EJD. In this video, our focus is on covariance and correlation, which is under joint distributions that we've been considering so far. So straight to it, we need to know what covariance is and what correlation is. But then covariance and correlation are measures that help us understand the relationship and dependence between two random variables. So as we talk about joint probability distribution, right? So we have at least two random variables, and it is important to see the kind of connection that happens between the two random variables and how one depends on the other. And that is the essence of covariance and correlation. So between two random variables. So while both deal with how two variables change together, they provide different insights. They provide different insights into the nature of their relationship. In essence, both covariance and correlation tell us how two variables change together, but each one of them has a specific way of telling us about that relationship. And that is why it is important to look at the specific, to look at each of them in turns. So talking about covariance, for starters, covariance, as you can see, covariance, that is like varying together. Covariance measures, so covariance talks about varying together, right? And correlation talks about their relationship with themselves, right? So covariance measures the direction of the linear relationship, linear relationship between two variables. Between two variables. Okay. It tells us whether the variables increase, whether the variables increase or decrease together. Or move in opposite directions. So if you have random variables x and y, so covariance tells us whether as x increases, y also increases, or as x is increasing, y is decreasing. Basically, that's what covariance is telling us. So, however, covariance does not provide the strength, does not provide the strength of the relationship, only the direction. So what we are saying in essence is that covariance tells you the direction of the relationship between two random variables, while correlation tells you the magnitude of the relationship between the two random variables. So the covariance between two random variables, x and y, is given by cov xy equals the expectation of x minus the expectation of x into y minus the expectation of y, like that. So it's, I mean, it's just like it's just like variance, except that in variance you have the same random variable relating with itself, but here you have two different random variables. So it's variance happening between two different random variables. So you can see the formula is basically the same, except that in the case of variance, you have x minus expectation of x squared. But here it's x minus expectation of x multiplied by y minus expectation of y. So here, where the expectation of x and expectation of y are the expected values, of x and y. Okay. And then we have the expectation of x minus expectation of x into y minus the expectation of y represents the expected value of the product of their deviations from the mean. So it bears close resemblance to variance that we saw before. So as you can see already, right? So x minus expectation of x is actually the difference between each the random variable and the mean value. So this is actually deviation here. This is another deviation for x, and this is deviation for random variable y, basically. So that's how that goes. Okay, so how do you determine what is really happening? So let's talk about interpretation now. How do you interpret covariance? Interpretation. So we have positive covariance, So when x and y increase together, increase or decrease together, then you can say you have positive covariance. For example, height and weight generally show positive covariance. Of course, this is logical, right? The taller a person is, the heavier the person would be because of at least the bone mass, right? So positive covariance. So when x and y increase or decrease together, then you say that is positive covariance. Then we actually have negative covariance. So for negative covariance, of course, as you can imagine already, that is when you have when x increases as y decreases, and vice versa. So if they are moving in opposite directions, in short, so x increases, y decreases, x increases, y decreases, or x increases, or X decreases, Y increases. That is negative covariance. For example, for example, um, for example, time spent, time spent on social media, time spent on social media, and productivity may exhibit negative covariance. Of course, the may is really important because if you're a social media marketer, for instance, the time you spend on social media should most likely translate to higher productivity. The more time you spend there, the more. But of course, if you get distracted and you're doing other things, then this might be true. So, but if you don't have any business on social media for the most part, and you are there for more time than you should be doing your job, then of course the time spent on social media and productivity will exhibit negative covariance because as the time on social media increases, your productivity would likely reduce. And as your time on social media reduces, your productivity will increase. So it's important to know why exactly you're on social media. Okay, so we have the third one. We've talked about positive covariance. The two of them either increase or decrease together. And we have negative, where they move in opposite directions. Then we can also have zero covariance. Zero covariance, no linear relationship, linear relationship, no linear relationship between the variables. So if you cannot say for sure what is happening between the two random variables, then you can say that they exhibit zero uh, covariance. So let's take maybe just an example. In the next video, I'm going to take some actual calculations. So let's say we are studying, let's say we are studying the relationship between hours studied, like hours of study, that's X, and the exam scores. So say, how many hours do you spend studying compared to the exam scores you get? So exam score is random variable Y, while hours studied is random variable X. For a group of students, for a group of students, okay. So if students, who study more, if students who study more tend to score higher, on exams, the covariance will be positive. The covariance will be positive. Okay, so that goes. Watch out for the next video where I'm going to do some actual calculation. Okay, so let's go ahead to talk about correlation. So covariance talks about the direction, of relationship between the two or more random variables, while correlation talks about the magnitude of that relationship. So both magnitude and direction in this case for that matter. So let's look at correlation. Correlation. So correlation standardizes the covariance. So I mean, it's like it goes the extra mile. The covariance already tells us the kind of relationship that exists, but it doesn't tell us the actual magnitude of that relationship. So correlation standardizes the covariance, making it easier to interpret. It not only tells us the direction, but also the strength of the linear relationship, of the linear relationship between two variables. The most common correlation measure, so it means there are many correlation measures, right? But the most common one, the most common correlation measure is the Pearson correlation coefficient. Pearson correlation coefficient. Okay. And it's usually signified by a rho. Um, okay. It's usually signified by a rho. Okay. The Pearson correlation coefficient signified by a rho, which is defined as this. So you have correlation of x and y equals the covariance between x and y divided by the product of the standard deviation of x and the standard deviation of y. So that's why we talk about standardization here. So the covariance now divided by the standard deviation. So here now we have that the sigma x and sigma y are the standard deviations of x and y. Okay, so then the Pearson correlation coefficient ranges from -1 to 1, such that if you have +1, that is perfect positive linear relationship. On the other hand, if you have -1, that is perfect negative linear relationship. Okay, so you can also have 0. 0 tells you no linear relationship. Okay, so in a sense, right, you can actually say, so you have 0, and then to the right you have +1, to the left you have -1. So this is perfect negative linear relationship. This is perfect positive linear relationship, and this is no linear relationship. So what happens in between? So it simply tells you that this side now is actually negative relationship, right? This is all negative relationship. And as it gets closer, so at 0, there's no relationship, right? But as it gets closer to the left, negative relationship is getting stronger and stronger, in this direction. Then in this direction now, it's neutral at 0, right? But as it gets closer and closer to +1, you have a positive, okay, let me say, uh, so you have negative linear relationship here, right? And it's increasing as it goes from 0 towards -1. And then you have the positive linear relationship, which gets stronger and stronger as you move from 0 towards +1. Okay, so let's take an example to drive that point home. So we have this Okay, let's take this example. So in the example of our studied and exam scores, we can calculate the Pearson correlation coefficient. So a correlation of plus 0.8 would indicate a strong positive relationship. Though not perfect, right? But it is strong. It's a strong positive relationship. Meaning students who study more tend to get higher exam scores. But the relationship is not perfect. You know, it will be perfect if it is exactly plus one. But the relationship is not perfect. So there's still some possibilities that, you know, somebody who studies a lot does not still get good scores, probably due to some other reasons. So that explains the imperfection in that. So let's talk about types of correlation. Types of correlation. Of course, I've mentioned it when I drew that chart of the with zero in the center. So like we saw that we have positive correlation. Positive correlation. That simply says that as x increases, y increases. Not both ways now. You know, in the case of covariance, right? If they either increase or decrease together, so that's positive covariance. But here now, positive correlation is strictly that both are increasing together. So as x increases, y also increases, y also increases. For instance, the correlation between income and expenditure may be positive. So that simply means that the more you earn, the more you're likely to spend also. So that's positive correlation. So strictly, both are increasing together. So no decrease together in this case now, as opposed to, as we see in the case of variance. So we have negative correlation. So for negative correlation, we have that as x increases, y decreases. Y decreases. Y decreases. So, for example, outdoor temperature, outdoor temperature, and the sale of winter coats may have negative correlation. So that simply means that you know, if the temperature is high, the need for winter coats is low, right? If the temperature is low, the need for winter coat is high. So that's a very perfect example of negative correlation. What about no correlation? No correlation. Okay. So the variables have no linear relationship. For example, shoe size and exam scores. Shoe size and exam scores typically have no correlation. So your shoe size probably most likely has got nothing to do with how high your exam score is. Okay, so we have that. So let's talk about the idea of dependence. Can we try to understand dependence? Understanding dependence. So because here we are talking about two random variables that have connections with themselves. Okay, so covariance and correlation help us understand dependence between two variables. So first, we have linear dependence. Linear dependence. So linear dependence occurs if the relationship between the variables so if the relationship between the variables is linear, covariance and correlation capture this well, okay? Capture this well. On the other hand, if we have nonlinear dependence, so see both covariance and correlation, both covariance and Pearson correlation may fail to capture non-linear relationships because in essence they are linear. So for which other methods like rank correlation, which is also known as Spearman's correlation might be used. So let's talk about an example. Okay, I guess I want to change now. So examples, or rather example of nonlinear dependence. Imagine that, consider two variables, x and then y now is equal to x squared. Okay, if you consider that variable, right? So although x and y are clearly dependent, so you can see there's a relationship between them. They are clearly dependent as y is determined by x. So y is a function of x. Y is determined by x. Okay. The Pearson correlation might be close to zero. Might be close to zero since the relationship is quadratic, not linear. And like it has been said before, it means that we may have to consider something like Spearman's correlation. All right, so can we do a kind of summary now? So, key points that you have seen so far about covariance and correlation. We have some key points. The first one is that covariance provides the direction of relationship, but not the strength. Okay, covariance just tells us direction. Two, correlation gives both the direction and the strength of the linear relationship. Okay. Then three, both measures assume linear relationships. So they are both linear in nature. They both assume linear relationships. So they might not fully capture complex dependencies. Okay. So let's look at some real life examples of this. Of course, just like I said, the next video, I'm going to take actual calculations. So all these ones are just still, some stories here and there. So look at the stock market, for instance, stock market. Okay. Covariance is used in the stock market. Covariance is used to measure how two stocks move together. So if stock A and stock B have positive covariance, they tend to move in the same direction. Direction. What that simply means that both increase or both decrease. Okay. So then we can talk about health data, right? Health data. So for health data, so in studying health data, correlation can show relationships between variables like blood pressure and cholesterol levels, indicating whether and how strongly they are related. Okay, so those are some real life examples right there. So watch out for the next video. I'm going to take actual calculations. So by understanding both covariance and correlation, right, you can actually gain insights into the dependence between variables, which is crucial for fields like finance, biology, engineering. Of course, here we have seen finance in talking about stock markets, and we've also seen it in biology or medicine, like where you talk about health data. So it can be applied in other cases. So watch out for the next video where I actually do some specific calculations. So if you have not signed up to this channel, you want to be sure to do that. Subscribe, and of course, hit the notification bell so you can always get alerted when a new video is released. Then don't forget to comment, like, and share. Till then, see you. Bye.